Okay, good morning, good afternoon, good evening, everyone. Welcome to today's ARMA Future Leader webinar. Joining us today is Professor Mostafa Mobasher, who is an assistant professor of civil and urban engineering at NYU Abu Dhabi. He received his PhD and MPhil degrees from Columbia University in Engineering Mechanics in 2017. And prior to joining NYU Abu Dhabi, he was an associate at Applied Science Practice in the consultancy firm Thornton Tomasetti based in New York. Now he is co-PI and the leader of the Energy Research Institute theme for sand hazards and opportunities for resilience, energy, and sustainability. Thank you so much for joining us. I know it's already late in Abu Dhabi. So with that said, the floor is yours, please.
Thank you, Bing. It's my pleasure to be here today. And I'm glad to get the chance to speak to you and the community about some of the things that we have been doing over the last year. So as you've seen in the ad, the presentation is about continuum damage modeling. I put here fluid-driven fracturing to kind of pick some audience, but it's really about modeling what happens in geomechanics failure and multi-physical processes in general. So before we get into the weeds, since you said into the details, since you said I'm on the other part of the world, let me just show you some pictures of our campus here. We're located on the beautiful island of Saadiyat in Abu Dhabi. We are a part of NYU Abu Dhabi is a part of New York University. It's a degree granting global campus of New York University. We have a beautiful campus here with excellent resources and interdisciplinary research. So if you are in the region for any reason, please let me know. I'll be more than happy to see you around here. Now, let me just fix the view. Yes. And also, as we are getting started, I'd like to introduce my team members who are the actual people doing the work. We have a great group of researchers, research scientists, postdoc associates, PhD candidates, and also visiting scholars in our group. And these are the real people who are doing the work. I'd also like to thank my former advisor who has contributed to some of the research that I'll be presenting today, Professor Chaim Weizmann from Columbia University. Thanks are due for him as I'm starting this research. Now, getting into fracture in rocks, which is our favorite topic for today. We see that in many applications, either in natural processes or in cases like man-made processes like hydraulic fracturing and carbon injection. It's important for us to live in a world that's safer, that's more resilient, and it's also important for several applications related to energy explorations, and more recently, the need to put the carbon in the atmosphere, bring it from the atmosphere back and put it somewhere under the ground. So there are many applications where we need to understand the fracture in rocks in order to be to do better engineering, to do better value engineering, and present better value to the community. Now, among the many challenges that modeling damage or fracture in geomaterials, among the many challenges that we see, these are probably the three that could be some of the biggest ones, and these are the interests of research in my group. The first one here is the need to understand that fractures are not just very thin lines between rock granules. They're really networks. They're networks of long-range cracks, microfractures that spread spatially and also spread across scale. And there are also networks of fluid flow. Depending on the material where the fracture is happening, there are capillary networks that happen across scales that transport the fluid from one place to another. And many of the currently existing models do not really account for that. So in the research that I'm going to present, we are proposing to account for these effects using non-local modeling effects for both of the damage processes as well as the fluid infiltration. The second challenge, which I'm sure many people are aware of, is the elevated computational costs. The more physics you put into the model, the more nonlinearity and the more thermal effects or fluid effects or whatever effects you add, the model just become prohibitive. We cannot train them anymore. So how do we address this? How can we leverage the newest tools to make this better? And the last one, which is not very well appreciated in the community, is understanding the energy budget. As I'll say later, many engineering applications, you cannot really design them without looking at what happens to the energy. Especially in hydraulic fracturing, we are applying energy to open cracks. Where does that energy go? Are we really opening cracks, or are we just dumping energy under the ground? So these are some of the topics that I'm going to speak about how we are attempting to model them today. To start with the thermodynamics approach for the long-range interactions, we start by postulating here. Yeah, I think there's an echo. Hope it's gone. Yes. Okay, start by postulating here this total energy definition. The first one is something that you probably have seen in Cauchy's book or in many other applications, the Helmholtz energy for the poroelastic domains. And then here we add two additional terms, which I'm going to speak about in a minute, and they represent the non-local strain and the non-local transport effects. And these help us understand what happens around the crack tip, help us understand what happens around this fracture process zone. And by working from here and introducing the first and second laws of thermodynamics, we can then derive analytically and compute numerically the solid and the fluid dissipation. Here in the work that I'm going to be talking about here, I'm going to be talking on the basis of continuum damage mechanics, which is a branch of modeling fracture. But the simplest thing for those who are not aware, here we assume that there is a scalar variable that controls the stiffness of the material. When this d variable is equal to 0, it's an intact material. When it's equal to 1, it's a damaged material. Now we proceed with the derivation. So as I said, the first term is the classical damage poroelasticity term, which has been presented in the literature before, and this is the expression for it. And then we have two additional terms, which depend on the difference between the local strains and non-local strains, as well as the gradients of that variable. And similarly, the difference between local volume of fluid storage plus and the difference between the local volume of fluid storage and the non-local volume of the fluid storage, as well as the gradient of that variable. And in order for us to introduce these additional energy terms, we need to also introduce some additional constitutive parameters. Now, in the limiting case, and we proceed with our derivation with the closest Duhem inequality with the first and second laws of thermodynamics, we arrived at modified stress-strain relationships and modified pressure zeta relationships. But in the limiting case, when we want these models to represent what we are currently modeling, if you take these models in the limit where these additional constitutive parameters go to 0, we actually see that these additional terms drop out, and we end up with two additional gradient relationships. The first one is for the strain or the stress regularization. The second one is for the non-local transport effect. So now let's look at each one of these. The first one is for the non-local, provides the non-local damage. So here, this is the stress-strain relationship. This is the pressure-fluid content relationship, and both are a function of damage. In this case, we start with a simplistic linear law for damage, but in other papers, we use other phenomenological models for damage, and we calibrate and validate these. And then we have a non-local equation, a gradient equation, which provides the non-local stress of which damage is a function of. And then we have the damage-dependent Biot's modulus and the damage-dependent Biot's coefficient. And the purpose of these relationships is to basically represent what happens in the fracture process zone. And this is a function of a region which represents the size of the fracture process zone, which is represented here by the variable g. Now, in the case of the non-local gradient, for those who are familiar with non-local gradient damage, this g represents the LC squared over 2, the characteristic length of the material, the characteristic length of the fracture over 2, which I think Professor Bazant has spoken about recently in one of his presentations. He's one of the founders of these ideas. Now we get to the less common concept, which is the concept of the non-local transport. When we put simply Darcy's law or even other types of fluid flow in porous media, we're basically assuming that the material is driven, that the fluid flow at the material point is only driven by the values of the stresses or the strains or permeability that we are calculating locally. In reality, porous materials do not work like that. There are scale effects, there are porous network effects, and several experimental and numerical models have shown that in order for us to understand better what's happening, we need a non-local transport, and there are different ways of doing that. Basically, we need to understand what's happening in the vicinity of this point and based on that, calculate where the fluid particle will go. Now we're dealing with Eulerian models here, so we don't really track a particle, but we still, in the totality, we can plot the streamlines of where the fluid goes in a hydraulic fracturing simulation. So here we are proposing this based on the thermodynamic derivations that I have postulated here. We can reduce them instead of the relationships on the fluid content. We can reduce them to a non-local permeability, which we then have extended to an anisotropic non-local permeability and the mathematical proof of here. And then after we have done all of this work, we actually found out that this relationship is very analogous to the Darcy-Brinkmann flow equation. And we actually realized that the size of this interaction zone is L squared, and this L squared would be equal to beta, which is the friction coefficient in the Darcy-Brinkmann flow. So we actually discovered this the other way around. We started from the non-local modeling idea, and we found that the resulting thing is very similar to the Darcy-Brinkmann equation, and the friction is kind of the friction coefficient in the Darcy-Brinkmann flow is kind of providing a very similar effect to what we're proposing with the non-local effect. At this point, we have formulated the strong form of the model. We know what are the effects that we want to model. These are the four governing differential equations. We can either model that directly as the four of them, or we can combine them by utilizing a stress-dependent permeability or permeability-dependent stress relationship and kind of reduce these to one. But in that case, we would be assuming that permeability grows in the same exact way that damage grows, which is an assumption. We have actually tried both models, the 3-field formulation and the 4-field formulations in different papers, and we have several parametric studies to show what's happening. One thing for those who are finite element specialists, when you get to these kinds of models, you know that you have to either use higher order elements or you need to use some stabilization to use equal order elements for both displacement pressure and the other variables. So in this model, we are actually using the stabilization proposed by White and Burha in 2008, by Joshua White and Ronaldo Burha, and it's a pressure projection stabilization. And this actually made our models work decently well for most of the cases. So first, I'm going to show some numerical results here for damage-enhanced consolidation. This is a simpler problem from a mechanics point of view than the complex hydraulic fracturing effects. We have a footing here sitting on some soil. We see here that in the beginning, the pressure is very high, and then we see the fluid exiting the system. And then as the fluid is exiting the system, damage grows. We have a local damage and a non-local damage. Our non-local damage achieves mesh independence, which is an attribute of non-local damage compared to the local damage, which is usually mesh dependent. And we see that in terms of the non-local permeability growth and also the fluid pressure growth. So this gives us confidence that the proposed non-local effects regularize the SOT effects in the model. And then we get into our main business here, which is modeling fluid-driven fracturing. So this is an idealized domain with some confining stresses. We start pumping fluid here. We get a damage evolution. We get an anisotropic permeability evolution. And here are some additional plots of that. So these two plots show what happens at the notch. So here we have the pressure increasing until it gets to the breakdown, and then it drops. Damage keeps increasing. The breakdown is pretty much around when the crack gets fully opened. The bottom plots here are along a section here that's a little bit ahead of the notch. And here we see that the fracture or the damage zone is quite localizing. It grows, but then it stays localized within the zone which we expect, which is usually a function of the non-local length scale that we're proposing. So this, among other things, other studies that we have in our papers, kind of gave us confidence in the model. It's achieving what it is supposed to achieve in terms of representing the physics. Now we get to the next question. What happens to the energy? Now we're pumping fluid, then we are spending energy here. Where does that energy go? I hope you're seeing my cursor. Okay, so where does that energy go? So if you go back to the initial diagram here, so we have a W external applied, and that gets to either spent either by an elastic energy that's stored in the system. Up to this point, our model does not have necessity, or energy that's being dissipated. Now we have two modes of dissipation in this model as it stands, as of theoretically postulated it. There is the solid damage dissipation, which is basically due to the fracture growth or the damage growth. And then the second component is the fluid viscous flow. And then we do here the first verification and validation study. So this is the W external, this is the W internal plus DT, they both on the top of each other. And then we see here that W internal, the internal storage, and DT are kind of, around the ballpark of little bit less than 50% of the total energy applied, which matches what we know from the experimental data. The experimental data on quantifying the energy is extremely limited. There are pretty much a couple of papers on AGU, and that's it. There's not much knowledge out there about what happens to the energy. Now, the question is, why is it interesting to learn about what happens to the energy? So if you look at other applications, we know a lot. So from projectiles to designing how things fly in space, all of that, we need to know the energy to understand what's happening, just starting from a simple ball drop. In applications which involve tremendous damage, like what we have in hydraulic fracturing, like car crash worthiness, knowing where the energy goes is pretty much everything. You need to design your system to dissipate the energy in a certain way. Well, in hydraulic fracturing, we also want our energy that we are applying to be used to stimulate the reservoir. We don't want to just spend the energy on just opening networks or just fluid viscous flow through the network that has been already opened and not get any bang on the buck that we're doing. And then which gets us to the fracture mechanics, and the fracture mechanics theories themselves are postulated from the concept of the energy. So how is the energy spent? That's the question that we're trying to answer. There are some, as I said, there are some studies out there, but really limited. This one is experimental. There is another one by our chair, Professor Bunger, that's also based on linear elastic fracture mechanics. So it does not account to fluid flow, it does not account to permeability changes, it does not account to the multi-scale networks that are happening. So there is a better need. There's a need for a better way to understand the energy budget in hydraulic fracturing. And this is what we're trying to do here. Since our model is based on thermodynamics, then we have access to these mathematical formulations. We can compute them numerically and see what happens. So let's start here by playing a little bit with the model that we have postulated. Let's take the Q, which is the injection rate, and increase it to Q, 2Q, and 3Q. And here I have two plots. One is the length of the fracture versus time, and the other one is the volume of the fracture versus time. Now, as you can see, which is the expected, the faster that you pump, the higher the Q, then the higher higher length you will get, let's say at the time of 0.2 by 10 to the 5 here, then you'll get a longer fracture and you'll get a larger volume. Okay, now the question is it worth it? Is it really the energy, the additional energy that I've applied, is it really going in the right place? So let's look at the energy. Now, when you look at this, you see that when we go from Q to 3Q, there is actually an increase in the energy that's being spent in the solid damage, which is the one that we're interested in. This is what we're interested in, to open new fractures. However, there is much more energy that's being spent. So look here, this curve, the scale here is by 10 to the 3, the scale here is by 10 to the 4. There's much more energy that's just being spent in the fluid viscous flow. Because what happens is that once you've started opening the fracture, there is an open network of tracks that, they're high permeability, so the fluid just flows. So in this case, depending on this model and the specific material parameters that we're using, you're actually, yes, you're making your cracks grow faster, but at what expense? At what efficiency? This is the question. Another thing, we started looking at this model and how will the fluid-driven fracture interact with pre-existing weak zones. And we consider two weak zones. The first one is we call it weak zone A. In this case, we have an intact stiffness, but a high permeability. This means that we have another type of rock material or geomaterial or soil material that has a higher porosity. So let's say going from a shale to a part, let's say where there is sand. So it's a high porosity zone, but it's still intact. It still has a high stiffness. The other one is pretty much an open fracture. It's a low stiffness, high permeability zone. So it's like a pre-existing fault, either a man-made or a natural. And we started running our model. We got the damage or the fracture contours, and then we compared them to fractal analysis and some acoustic emissions. Our results are pretty much on the same ballpark. We see the same fishtail trends. We see the same trends overall. Again, there are more details here on the specific verification and validation that you can find in these papers. But for the sake of discussion, let's get back to what happens with the energy. What you see here is once you get to that point, yes, there is damage growth, but it's really minimal. What happens is that once you get to interacting with this pre-existing fracture, most of the energy is being spent in fluid flow. And you don't really get much by continuing the pumping in that area. So this kind of simulation might be useful to understand. I'm not saying that these are the final results or these are the final conclusions, but I'm saying that now we have a tool that will let us look at the flow-driven fracturing from another perspective. Let's look at the energy. Let's look at the money that we're spending into pumping. Where is it actually going? Are we actually gaining what we are trying to gain from this? We took the same model and we started extending it to more complex material properties. We understand that in some cases, viscoelastic effects, time-dependent effects are important. So we calibrated the model viscous parameters to with triaxial testing data from the literature. We calibrated the parameters, and then we started testing with different ratios of initial permeability and different values of viscous response. Here we have different values of permeability anisotropy. So n equal 1 is totally isotropic until it goes to n equal 20. This is very anisotropic between the vertical and the horizontal direction. And then we started looking again at the energy. And here we are seeing different things. We're seeing that, for example, with n equal 1, you're seeing the highest damage energy dissipation, and you're seeing the highest viscous dissipation. So, and then that response changes according to the anisotropy of the permeability itself. So again, what we're trying to say here is that accounting for the time-dependent effects and accounting for the anisotropy could be something else that we need to consider when we are looking at the energy dissipation, because the energy dissipates now in this case in multiple ways. We have the solid fracture, we have the fluid, the viscous flow, and we have the solid response, the solid time-dependent response as well. So to conclude this part, what we are trying to say here is looking at the fluid-driven fracturing with the lens of the energy budget could be enlightening and could be showing us some different physics, different from what we see just by looking at our traditional models, especially those who are the ones that are dominated by just linear elastic fracture mechanics. Once you start including these additional linearities in the model, then you start getting better insights. Now, if I'm a practical person, and as being said, before coming here to NYU Abu Dhabi, I used to work for the industry. Okay, this is great. All of this is great, but these models, we cannot run them in practice. Period. They're very expensive. They're very expensive to create. They're very expensive to run. The size of the domains that we're considering here are very unpractical. These simulations take hours, days, maybe weeks, and sometimes to get a reasonable answer. So what are we going to do about it? Which brings me to the next step. Our group has started a new endeavor, which we call integrated finite element neural network. Basically here, we're trying to leverage neural networks not to replace what we are doing with the typical analysis. We're trying to use them to improve the current state of the art of nonlinear and multiphysics models. So basically here, this is a typical finite element solver subroutine or typical finite elements solver framework that you go into incremental dynamic loops, and then for each dynamic loop, you have iterations until you get to convergence. You update the solution vector and then go to the material model, calculate the new stiffness, compute your Jacobian and residuals, and then go and so on and so forth. Okay, what if I tell you that I can plug a neural network here that can help you do that and get to convergence faster, or can take off some of the computational load that the finite element has to do itself. But keep in mind that this neural network will still sit within the same framework. So it's not going to give me an answer just based on the network predictions. It's going to give me an answer based on the minimization of the residual, which represents the weak form, the residual equation, which then confirms to the physics that we are trying to solve at the end of the day. That would be, in our minds, that would be great. So now, what are we going to do about it? This is what we started doing. So we started looking at, as I said in the beginning, we were doing non-local damage. In the equations that I showed earlier, these were stress dependent. Here we're talking about strain-based non-local damage. It's pretty much the same formulation, whether you go from strains to stresses. It just depends on the underlying phenomenological models. So we have the local damage, which, as we said, it can be lower in the computation cost, and that gives you damage localization and mesh dependence. Now you'll go to the non-local gradient model. It's mesh insensitive, but you have an additional cost, which is, one of the costs of the additional physics that we're trying to bake in the model. Okay, what if we say that we're going to eliminate this, and instead of using finite elements to solve for that additional degree of freedom, we'll just use a neural network? So this is what we have done. We trained a neural network to basically represent this equation using a physics-informed neural network. In this case, we're talking about a sequential MLP multi-layer perceptron networks for every time step, which is, of course, very expensive, but we're going to improve that in a second. To do the mapping between the local strain and the non-local strain. And once the non-local strain is calculated, then it is plugged again into the same elasticity equation, damage equation that we have. So by doing this, we have eliminated the second equation. We've reduced the size of the system of equations that we're solving. We're solving the same system. And while we're doing this, we are predicting the non-local strain and also its derivative here and plugging it. Now, the actual test of whether this is working will be, well, does this IFN system converge? Does it work? Does it give us the right answer? Which we'll see in a minute. But before that, this is the detail of the MLP that we're using. This is not the exact size of the networks. This can be found in the paper, but this is just an idealization. So here our input are the locations, the X and Y, the coordinates, the local strain, and then the output is the non-local strain and its spatial derivatives, and also the derivative of the output with respect to the input, which we are going to use for the Jacobian calculation. And then we start using that to model, the first problem here, like a single notch tension problem. As I said, here we're doing sequential MLP. So for every time step, we're training a specific network to predict that, which of course is very unpractical, but it's our first step as a proof of concept. Now we start looking at this. So these are our true predictions. These are the predictions of the network. These are the errors, which are very minimal. But more importantly, this is what I see as impressive from this study. We actually get convergence. So actually, that system that we are proposing works. We were able to replace the material model or just a part of it by a neural network and still keep the cycle going. This will be very advantageous once we have the right type of network developed. So at this stage, our observations, the errors are remarkably low. There is convergence. In some cases, like the specific snapshot that we're looking at, the convergence of the IFN setup is even faster than the finite element. So it's faster in multiple ways. Now the question is, how can we do all of this with a single network? How can we train just a single network that can do this problem for us for different loading cases? Which what got us into what we call now the physics-informed temporal convolution network. Now, this is another type of a sequence-to-sequence modeling that we introduced it to learn physics as well. I don't think we have the time here to explain the specifics of the temporal convolution networks, but again, this is in the literature, and this is not something we came up with. The temporal convolution networks were there. We made them more enhanced by introducing the physics-informed character to them, and then we involved them again into our finite element analysis procedure. And then we started solving the same problem again. So for the same problem, again, we're seeing very consistent conversions. We started seeing time savings, which here are not great, but they are starting points. So we're talking about 10 and 20% in the very first trials of the method. This is something that we can build on. We started modeling other geometries, other loading conditions. So here we have a shear loading case. Again, we started seeing interesting phenomena. Overall, the IFN is taking less time. What we also realized is that it's also more robust in some cases. So, as our cracks get longer, as our damage zones get longer, we usually have convergence issues. Sometimes the finite element models do not even work. They are not unable to give us results, or they take too many iterations or too much time per increment. What we have seen is that the IFN here it actually, even when finite element is struggling, when we try different solvers, DiFan is doing pretty well, and it's giving us a very efficient solver at the end of the day. So now we have done this for non-local damage. We are currently working on developing this for poor elasticity, but before that, we wanted to try with a little bit a distal version of that. So we started with thermal elasticity with introducing thermoelastic effects. So again, the idea is very similar. We are solving the mechanical weak form. We're solving the mechanics problem, and we're using the neural network to predict the temperature and plug it back into the mechanical equilibrium equation as an input and use that to solve the problem. This is our first trial problem here, just a plate with some boundary conditions, and we're getting very interesting results. Basically, we're training the model on a coarse mesh of 700 elements, and then we're trying it on a 7,000 elements model. And this is something that we usually need in practice. In order for us to resolve the stresses and know what's happening at the crack tip, we usually need very fine meshes. But in some cases, modeling such physics on their own can be done on coarser meshes, and these two solutions can be combined. So long story short here, finite elements is taking, for example, in this case, 36 seconds, where IFIN is taking 18 seconds. So we wanted to test this further. We extended this not only with the PyTCN. We have another paper coming up where we introduced a network that learns from the variational form. So it learns from the energy principles of thermoelasticity, which we think will be very valuable once we get to poor elasticity as well. We also tried to replace some of the automatic differentiation that the neural networks are usually based on into learning using some pre-computed shape functions, since we already have the finite element models, or we have access to them and we can use them. And long story short, you can see that, yes, in the smaller models, finite elements is usually faster, but our IFIN scales pretty well. And it gives us, as the size of the models increase, IFIN becomes significantly faster. And you can see here, these are our initial trials. SFAD is the first model, and then we're going further and further downward, and we kept becoming more competitive with the finite element solutions. So this brings me back to the starting point. There are three challenges that we are trying to address in this research. The first one is representing the long-range interactions in terms of the damage mechanics or the fracture mechanics. The second one is the elevated computational cost. The third one is understanding the energy budget. For the first one, we are here producing or proposing non-local models to help us understand what happens around the crack tip in terms of both of the fracture, the damage, and the fluid transport as well. And we're able to verify and validate that model against some of the available experimental data. We have started using this model since it's formulated from thermodynamics principles, so we are able to analytically derive the energy storage and the energy dissipation analytical formulas, compute them analytically, and start getting insights from them. So we have presented that as well. And then realizing that as we are adding more physics and as we are adding more nonlinearities, our models become very expensive. So we're now working on this new idea called IFIN, integrated finite element neural networks, in order to limit the cost of these simulations. And it's all work in progress. That's it. Thank you so much for listening this far. And I have some references here, but I think it will be very hard. So this is a QR for those who want to access our papers. This links to our group website. Feel free to email me about any questions, and I'm available for any questions right now. Thank you so much.
Thanks so much for this talk. Very concise, and also tying it back to the original concept that we're trying to solve, which is always clear for people like me who are not from the finite element world. So thank you so much. So with that, if there are any questions from the audience, please feel free to leave them in the chat, or simply just unmute yourself, share your video if you're comfortable. Shazad, did you have a question?
I just wanted to say it was very impressive, Mostafa. We have a lot to talk about because I just wrote a proposal on these concepts, but not as impressive as yours. This is amazing. I'm gonna read your papers and meet you in ARMA. I have to
Yes.
go, and I have another meeting in 5 minutes to get ready for that. Thank you
Thank
so
you,
much for
Sharzad.
all
See
this,
you. See
being
you in ARMA, and feel free
available.
to reach out. Thank you so much.
Thank you. Bye-bye.
Thank you. Bye bye.
Any other questions or comments from the audience? If not, of course, I'm very curious about this too. So on slide 17, you show the damage zone quantification, and you're focusing more on the length of that damage zone. I'm wondering if you
You're
could,
seeing, you're seeing slide 17.
yeah, 1-7. Um,
Yes.
yeah, you were talking about the evolution of that damage zone. I was wondering if you could talk about the width of this damage zone. Is it sort of consistent across the geometries or materials and all that?
So that will depend on several variables. It will depend
Mm,
on the permeability, how fast it changes. It also depends, in this case, in this specific model, on the values of the length scale that we use. So we have this. Okay, let me get back to this. You see here we have two equations. One is for the non-local stress and one for the non-local permeability. And the non-local stress is what governs the damage. And here we have, in the case of constant, we have constant and non-constant length scales. But basically, this width of the damage zone will be governed by these two length scales. And we have here this paper in 2021, which has a specific study on what happens when one is different than the other. And you see that in some cases, damage overtakes, but then it stops at certain point if permeability is not going that far, because if you don't have fluid going that far, then nothing will open the crack. And the same way otherwise. But we see a stronger effect from the permeability length scale than the damage length scale, because when you have a larger length scale for the permeability, then you have fluid going in further places. This is true in the beginning of the fracture, so closer to the tip, closer to the notch. Now, as you go further, it kind of develops its own. I don't want to say it's steady state because it's still a function of time, but kind of develops its own new equilibrium. But we have in that paper, 2021 paper, we have a very detailed study on the interaction between these length scales and what would they do to the damage zone, to the permeability zone. And this is something that I probably didn't say. Now, when you do a linear elastic fracture mechanics model, usually you have an open crack and you calculate the crack width and then put the fluid inside it, and then the fluid will exert pressure on the sides. This is how you present a hydraulic fracturing in this context. Now, here we represent the fluid fracturing by basically a disturbance to two fields, a disturbance to the damage field and a disturbance to the anisotropic permeability evolution. And you cannot really see one of them without the others. Remember, in the old days when you used to have, transparent plastic slides, you need to overlay both of them, look at them together, and this is what will tell you what is happening to the material. What exactly, now coming back to that real picture from the beginning, it could be, for example, depending on the type of the material, the inherent anisotropies and homogeneities, the way you frack it, the way you're applying the load, you could have different setups of these two networks. One of them could be larger than the other. It also depends on the multi-scale porosity networks. So now this idea of non-local transport coming here, these capillary networks can be very, very long. And they basically change the pressure gradient, they change your overall permeability, and will change how your fluid grows. So just looking at a single material point, we found that to be kind of not very representative of what happens in reality. You need to kind of use a larger lens to understand what's happening.
Okay, very interesting. Cool. So the non-local transport is not phorelasticity. It's simply pressure gradient that's forming in a very predefined path, essentially.
Yes.
Okay.
Yes.
Okay. Oh, okay. Okay. Very cool. Sorry, I'm kind of dominating the conversation. Any questions from the audience? Once again. Okay. If not, I have one more. That's curiosity point. In the pin, the second one,
Yes.
is that still being trained per geometry, or has it come to a point where it's a general pre-trained network for
Yeah.
for any?
So everything that I've shown so far
Mhm,
is trained for a specific geometry. We have ways of dealing with that, but
mhm,
and there are some methods in the literature that people have started doing that.
mhm.
But we see bigger ticket items at this point. So
Okay.
there are mapping methods and things that you could do to go like to make it learn on one geometry or on boundary conditions. There are operator networks that can help you do that. There are mapping methods.
Mhm,
But we are seeing a fundamental issue with predicting phenomena over time. So right now, basically, the two options available are either
mhm,
using sequential step-by-step networks, which basically you have to train a step for every network. And these
mhm,
networks manage to predict very well and interpolate very well in both space and time, and can some even in some cases extrapolate. But it
mhm,
doesn't make sense to train a network for every time step. This becomes, defeats the purpose.
mhm,
So once you start going to sequence models, which can predict over time, they have
mhm,
some deficiencies. So they just predict sequence. They were not made for our applications. They came from, let's say, text recognition. They came from predicting, lingual things. They are not our problems. We want to have functions that we can use. We need an f of t to be able to
Yes.
understand what happens between t1 and t2. So
Yeah.
we are now working with some new other approaches fundamentally different from sequence to sequence. And
Mhm,
we're seeing some preliminary results and we're seeing some preliminary challenges also. And we're seeing this as our bigger ticket items. But the question that you said about the geometry and the boundary conditions is also very interesting. Now, let me tell you
mhm,
something. Specifically, hydraulic fracturing could be one of the most suited problems for this type of IFN formulation.
mhm,
This is simply because, in most of the cases, our geometries look the same and our boundary conditions do not vary that much. They vary from place to another. The confining stresses could be different, but they don't vary that much. It's not, for example, like I'm designing a car, so every car will have a different geometry. No, at the end of the day, we work with planes or 2D planes or 3D planes.
yeah,
And, there are end conditions. There are confining stresses that can have different values. There
mhm,
are measures of anisotropy that we can make the model learn and randomize with some probabilistic infusions into the model, and we can get away with it. So I think this field of geomechanics is a very, very good candidate, and there is a lot to be done with neural networks in general and with this IFN approach.
very cool. Richard, you had a question, please.
Yes, very good talk, Professor Mobasher. I was wondering if you had any familiarity with mixed neural network finite element methods, where instead of representing the displacements or velocities using polynomial functions, we represent them using neural networks. These
Yeah.
formulations are touted to be more efficient than using standard finite element techniques. So
Yes, so there are a couple of them. There is a hybrid, at least the ones that I can come to my mind. There is one that is called actually very similar. It's called HFIN, hybrid finite element neural network method, and there's
Mhm.
another one that's called DEM, deep energy method, and both of them are kind of doing what he said. They're basically replacing the approximation functions with networks. Now
Mhm,
they're very good, and the papers are very promising. Now, from hands-on experience, these methods they become difficult to scale when you have more practical and more difficult problems, more nonlinear problems, more realistic. So when you see the papers, they look very impressive on small problems, toy problems. Now start introducing something more difficult that doesn't work
Mhm.
because they lack. And this is my opinion. Don't take it as a fact. This is what our experiences have led us to. They lack this framework. So finite element has been there for, I don't know, 40, 50, or 60 years. And this idea of the rigor of the nonlinear solvers and the multiphysics solvers has been developed step by step. And it all counts on the minimization of a residual function. So at the end of the day, we convert the strong form, the partial differential equation, into a weak form, and we minimize that form to 0 to make sure that we're actually solving the problem. So this is the objective of the nonlinear model. You can call it the objective function of the nonlinear finite element model, is to minimize these residual variables. Now, if you do not bake this into the methods that you have mentioned, then there is no guarantee, no matter how well you train them, that in more difficult problems, there's no guarantee that they're going to fail or not. And this is from hands-on experience, because we have, I cannot say that I tried myself, but among our, this big team of people who came from different backgrounds and who have put their input into our research mix. And this was basically their input, that when you start, some of the people here have written some of the most impressive papers on, for example, deep energy methods or other methods. And the input is, if you take it to a more complex problem, it doesn't really work.
Okay. Thank you.
Thank you. Thanks for the question.
Any other questions from the audience? Please do not be shy. Or please leave it in the chat if you are shy. Okay, if not, we'll cut it off there. Thank you so much for this presentation. And look forward to seeing how a lot of this progresses.
Thank you. Thank you so much, Bing and Wei, for the opportunity. Thank you for the audience. We can also, I think all of us can say special thanks to Professor Zimmerman, who has joined us today. So thank you all. I appreciate your time.